Good morning, students. Myself, Vijay Shankar from the department, Chevrolet Engineering College. Today, we are going to discuss about the second unit Fourier series, the signal set system. Subject: second unit Fourier series. Already, we completed the brief description about the second unit. What are the different conditions and discrete conditions? And what are the different types? So again, you can see this. For Fourier series, a continuous time Fourier series purpose is Fourier series is used to analyze periodic signals. Fourier series is used to analyze periodic signals. We know the periodic signals for the x of t is equal to x t plus the x of t is equal to x of t plus capital T for the continuous, or otherwise in the discrete time function means x of n is equal to x of n plus capital N, where capital T is a fundamental period and capital N is also the fundamental period. But this is for continuous time function. This is for the discrete time function. Okay. So Fourier series is used to analyze the periodic signals only. The periodic, it is repeated for regular intervals with the time period of t or the time period of n. Okay. The harmonic constant of a signal is analyzed with the help of Fourier series, and the Fourier series can be developed for continuous time as well as for the discrete time signals. There are three types of Fourier series we have. Trigonometric Fourier series, compact trigonometric, it is also called as a polar Fourier series. And third one is an exponential Fourier series. Exponential Fourier series. In the last class, we discussed about some of the discrete conditions. One is a single valued property, having only the one value for the t values. Suppose these are like this, having only one value. The single valued property and must be absolutely integrable. Integral x of t dt is less than the infinite, and it having the finite intervals and finite peaks and finite discontinuities. These are the four we have in the discrete conditions, which satisfies this square integral linear over one period. X of t must be absolutely integrable, that is integral x of t dt is less than the infinite. If any finite interval of time x of t is bounded variation, that is, there is no more than the finite number of maxima and minima during the single period of the signal. If any finite interval of time, there are only one finite discontinuities. For this case, for this class of signals, we are able to express the linear combination of the complex exponentials. The complex exponential x of t is equal to sum of k equal to minus infinite a suffix k e power minus j k omega naught. So clearly explain the last class what are the different conditions we use. These are the necessary conditions, but not the sufficient. It's sufficient but not necessary. So sorry, it is sufficient but not it is a necessary conditions. Okay. And see the continuous time Fourier series coefficients, the Fourier series coefficients we have here. The x of t signal, the sum of k equal to minus infinite to infinite, a of k e power j k omega naught t, where omega naught is a 2 pi by the t, the angular frequency, and the coefficient is it is given by the a k is equal to 1 pi to the integral t x of t e power minus j k omega naught t dt. What it matters to us. And it is only for the periodic signals. The periodic signal condition is x of t is equal to x of t plus capital T. And we already derived these expressions a of 0 and a of k and b of k in the previous class. It is also the 2 pi t, my students. 2 pi t the integral x of t dt, and 2 pi t the x of t cos k omega naught t or cos n omega naught t when I am taking the a suffix n, and Pn is equal to the 2 pi t the integral of t x of t x n we can take here instead of k n omega naught t, both are the same. Is the a0 is equal, and trigonometric Fourier series the expression is 3 terms, a of 0 and sum of k equal to 1 to infinity a of k cos k omega naught t, and sum of k is equal to 1 to infinite b of k sin k omega naught t. Okay, is a trigonometric Fourier series. Now the next one is so the trigonometric Fourier series will derive from the equation of f of t is equal to sum of n is equal to 1 to infinite cn xn of t. This is the equation we got from the orthogonality expression for the right angle triangle. The e of t is very small, the f of t the signal, and the cn xn of t. Cn xn of t according to the right angle triangle, the hypotenuse f of t is equal to the e of t plus cn into xn of t, where n is 1 to capital N. Otherwise, the error signal is very small and it is approximately equal to the sum of n is equal to 1 to n cn xn of t. This is the equation we got from the orthogonality function. The right angle triangle considers the two signals and the approximation signal, the xcn xn of t, and there is an error signal e of t is very small. The f of t is equal to approximate signal. And we have seen that in this function, the set having the 1 cos omega naught t, cos n omega naught t, and sin omega naught t, and so on, sin n omega naught t. Take the a naught is a value, the a1, the coefficient, a2, and so on, the cosine functions. P is a coefficient for the sine function. So rewrite this function x of f of t is equal to a naught plus sum of n is equal to 1 to n, a n cos n omega naught t, and b n sin omega naught t. So the cn is equal to, according to the orthogonality of approximation signal, is the equation we have, cn is equal to. That we can take that cn as an here, an f of t, and the xn of t is considered as a cosine function, and the denominator is a cos n square of cos square n omega naught t. After deriving that, we'll get the 2 by t naught into the integral t to t plus t naught is a full cycle. F of t into cos n omega naught t dt. Cos n omega naught t dt is an is equal. By substituting of n is equal to 0 here, a0 will get k of 0. That is also the 2 by t naught integral t to t plus t naught into cos 0 is a 1. So f of t dt. F of t dt. Okay. The same function we got here. So cos n square omega naught, after that deriving the expression, we got the t naught by 2, and it is the denominator. I'll get in the numerator the 2 by t naught. An is equal to 2 by t naught integral t to t plus t naught f of t cos n omega naught t. And the a naught is equal to, here you can take the 2, my dear students. Some mistake is there, the 2. Otherwise, you can keep the a naught by 2. A naught by 2, and it is a 2 by t naught. Otherwise, it is a 1 by t naught means it's a naught. A naught by 2 by keeping of 2 by t naught here. Otherwise, 1 by t naught, but change this function as a naught by a naught. Okay, same the bn is also the same thing. The integral sine square n omega naught t in the denominator. Cos square omega n omega naught t means 1 plus cos 2 theta, 1 plus cos 2 omega naught t dt by 2. And the sine function is also will become the 1 minus cos 2 omega naught t by 2. So in full cycle, the cos interval integral is always a 0, and for the one with integral with the t, upper limit is a t naught Divide by 2 here, the T naught by 2 for both the conditions. So Bn is also, we have the 2 by T naught of integral T to T plus T naught. The numerator is f of t is considered as a 1 x of t, and sine n omega naught to t. When I'm changing this as f of t as x of t. So x of t having a naught or otherwise a naught by 2 by keeping the 2 by t naught here, or a naught is 1 by t naught, and here it is a naught. Remember, this is a very important expression. The x of t is equal as a trigonometric Fourier series. Same thing. The second one is a compact trigonometric Fourier series. Compact means it is a polar form. The previous trigonometric Fourier series is a rectangular form. Now convert that into the polar form. The rectangular to the polar, it having the magnitude and the phase. What is that magnitude we have? The magnitude, the d of k is equal to under root of a of k square plus b of k square. A of k square under b of k square. Phi of k is a minus tan inverse imaginary term coefficient by the real coefficient, the b of k by the a of k. Now the rewriting the x of t, the rectangular function, the t of 0, a of 0, whatever we have, and combine the two functions, the sine and the cosine function as a single term by taking off the d of k is a magnitude of a of k and b of k, and the phase angle pi of k is equal to minus tan inverse b of k by a of k. Okay, converting of a of 0 plus the sum of n is equal to 1 to n, 1 to n, a of k cos k omega naught t plus sum of n is equal to 0 to n, or the 0 to 1 to n only, but the 0, the value is 0 only. 1 to n, b of k sine k omega naught t. This is x of t equation. It's a trigonometric Fourier series. Converting this trigonometric Fourier is a compact trigonometric Fourier series. E of k and b of k is a magnitude, is a d of k, and the b of k, the ratio of a of k taking off minus tan inverse is pi of k, the angle. Rewrite the expression x of t as t of 0, the same as a of 0 here, 1 by t, the integral t x of t dt. Otherwise, it is a 2 by t, 2 by t, and keep here the t naught, t of 0 by 2. And sum of k is equal to 1 to infinite, t of k cos k omega naught t plus pi of k. Okay, this is a compact trigonometric Fourier series. So most of the analysis of the Fourier series, we are not using the compact trigonometric Fourier series equations. Only can use the exponential Fourier series. One is a synthesis equation and another one is a analysis equation. These two only we are using to derive the properties of the Fourier series, whatever it is. The compact Fourier trigonometric Fourier series we are not using. Okay, and the discrete conditions, what we explained in the previous class, the 4 we have single valued property x of t must have only one value at any time instant within the interval of t naught. Before that, it is a see the what is the exponential Fourier series. X of t is equal to, remove this, x of t is equal to sum of k equal to minus infinite to infinite x of k e power j k omega naught t. And actually, this analysis equation of the Fourier series is this one, and the Fourier series is for only the periodic functions. So it is a 1 by t, the integral t, 1 by t, the integral t, e power minus j k omega naught t dt, and here x of t is also there, my students. Little bit mistake is there. The x of k is equal to 1 by t, the integral t, x of t into e power minus j k omega naught t dt. So what is the x of t? Is a coefficient. Exponential Fourier series, the x of k is a coefficient of here. So x of k is x of t is equal to, it is a sum of k equal to minus infinite to infinite, x of k into e power plus value of the synthesis equation, e power j k omega naught. So remember these two equations, mostly all the properties is derived by using these two equations, so analysis equation and the synthesis equation. Analysis equation, once again, x of k is equal to 1 by d, the integral t, x of t into e power minus j k omega naught dt. And the synthesis equation is x of t is equal to sum of k equal to minus infinite to infinite x of k e power jk omega naught dt. It's a positive exponential, here it's a negative exponential. Okay. The discrete conditions which are sufficient but not necessary here: single valued property and finite discontinuities within the interval of t naught, and finite peaks and within the interval of t naught, and absolutely integrable. So the finite integral single valued property means it having only the single value. The function having only the single value at the t naught here. See the double valued x of t signal and single valued function. And another one is finite discontinuities. You see here, there is no, in the first one, there is no any finite discontinuities here. And here there is a finite number of discontinuities, or the number of 0 to 0, 0 to t. Again, it is a repeated and again it is a repeated. And here it is a fixed maxima and the minimum number. Here also the finite maxima and minima, finite peaks. In this, there is no, in the first one, the first diagram, it shows that there is no any fixed maxima and minima. There is a changes here and here there is a changes. And but here there is a fixed maxima and minima, it's a peaks. And similarly, the last one saying that is absolutely integrable. Absolutely integrable. First one it shows it's not absolutely integrable, and it is a absolutely integral function, the integral 0 to t x of t dt as less than the infinite. And these functions, discrete conditions, and these discrete conditions are sufficient and is not they are not the necessary one. So sufficient and they are not the necessary one, my dear students. Okay. Now see, there's a very important topic here. Properties of Fourier series. The properties of Fourier series. The first one is a linearity property. The first one is a linearity property. In this linearity property, what is the statement saying that if x of t, the Fourier series is x of k, and the y of t, the Fourier series is a y of k, then you can prove that the z of t is equal to a into x of t, b into y of t. Let this function is also the x1 and x2 also, you can prove that function. Z of k is equal to a into x of k and the b into y of k. To prove this function, you can use the analysis equation, saying that is analysis equation. We'll explain the whiteboard by the students. See the saying here, the statement saying that the x of t is a Fourier series. X of t, the Fourier series is x of k, and y of t, the Fourier series is applying the Fourier series y of k. Okay, y of k. Then you can prove that the combination of the signals a into x of t plus b into y of t is a Fourier series of Fourier series a into x of k, a into x of k plus b into y of k, b into y of k. For that, we can take the so one of the first property, property 1. So linearity property, the linearity. By taking the analysis equation, by taking the analysis equation. What is that analysis equation saying? That the x of k is equal to the capital X of k is equal to the in 1 by t, the integral t. The limitations is the t limitations, and x of t e power minus jk omega naught t into d is the analysis equation, my students. So what is the x of t? Assume this is the x of t signal. Or little bit confusion here also, the x of k is there and y of k. So I am taking the x of k as a z of k. Okay. To avoid the ambiguity here, the 1 by t, the integral t, and the x of t as I am taking the z of t as a time function and the frequency. E power minus jk omega naught t dt. Okay, this is equal to that of z of t. As of the function z of t can take a into x of t plus b into y of t. Now we can prove this is a z of k is equal to a into x of k plus b into y of t. So first of all, you can substitute the equation here. The integral t, z of t is a into x of t plus b into y of t into e power minus jk omega naught t dt. Now split this integral into two parts. The first part 1 by t, the integral t, a into x of t, a into x of t, e power minus jk omega naught t, jk omega naught t into dt is the first integral, plus for the second integral 1 by t, the integral t, b into y of t, e power minus jk omega naught t dt. Now observe the equations, the two terms here, x of t e power minus jk omega naught t dt, the 1 by 2 integral is nothing but x of k. And here the y of t e power minus jk omega naught dt is the integral with 1 by t is multiplied. So y of k. And having the constants are there, a into x of k, the total equation as per the definition of the analysis equation of the trigonometric Fourier series, exponential trigonometric Fourier series, we can call it. And plus, and the p is a constant, and 1 by t, the integral y of t e power minus jk omega naught t dt is a y of k. So a into x of k plus b into y of k is a z of k is equal to. So linearity property, by taking off the two signals x of t and y of t, by adding the two signals with the constants of a and b, apply the Fourier series to get a into x of k plus b into y of k. The first one, the first property, linearity property. Then you can see the second property, time shift or translation. Time shift and the translation. Second property. What it matters for time shift and translation, or time translation, simply saying that. So in this, the statement of the time shift property saying if x of t, the Fourier series is x of k, x of t, the Fourier series is x of k, then taking the z of t is equal to, taking the z of t is x of t minus t naught. The time is shifted with the t naught samples. The time is shifted with the t naught samples. And in the frequency, the z of t is equal to whatever the times number of samples is shifted in the time, you'll get as a negative exponential with that T naught only samples, e power minus j k omega naught into T. Actually, the T is getting of the T naught samples and it is multiplied with the frequency of the signals x of k. Let's you can prove this time shift of the translation function. Now we go the second the property 2 time shift property. That is a time shift property. What is the statement saying that the x of t or the z of t, that is taken. For a little bit confusion, if you have to take the x of t, z of t is z of t minus t naught. The time is shifted with the t naught samples. Applying the Fourier series, you'll get z of s, z of k is equal to e power, the exponential value, e power minus j k omega naught into t naught. Remember this, into t naught x of t. For x of t, the Fourier series is, if x of t, the Fourier series is x of k only. When it is shifted with the t naught samples, it is multiplied with the e power minus j k omega naught into t naught. To take the proof, we know the z of k is equal to integral 1 by t, the integral t x of t into e power minus j k omega naught t dt. These are formulae for the analysis equation of trigonometric, not the trigonometric, exponential Fourier series. So what is it is not the x, my student, sorry, the z of. So 1 by t, the integral t. Take the z of t as the x of, not the x of, z of t minus t naught into e power minus j k omega naught into t dt. So sorry, this is not the z also, it is an x only. And here also you can keep this x. Assume t minus t naught is equal to some m. Got it, my students? So t is equal to m plus t naught. The t naught is a constant. Apply the derivative on both sides. So dt is equal to dm. So 1 by t, again, the integral t. Now what is the x of t minus t naught? It becomes of x of m. And e power minus j k omega naught. Now the t is replaced with m plus t naught. Into dt is replaced with the dm. So this exponential, again, two parts will get. One part is a 1 by t into integral t. I'm writing it as x of m into e power minus j k omega naught m into dm. And another part of the exponential is e power minus j k omega naught into t naught. So observe here the 1 by t, the integral t xm e power minus j k omega naught into dm. Again the same function here. With the variable of z here the x, z, here the x, and the variable is a t. Instead of t here the m. X of m e power minus j k omega naught m and the dm. So it is the same as z of k. Instead of z t, the x is x of m. So it becomes of x of k into e power minus j k omega naught t naught. This z of k is equal. Okay. So z of k is equal to, it is multiplied with the e power minus jk omega naught t into x of k. Understood, my students? So time shift property, the z of k is equal to e power minus jk omega naught t naught into x of k. Omega naught t naught into x of k. Now another one is a third property. The third property saying frequency shift property. Previous property is shifting in the time. Now the third property is shifting in the frequency. How many samples here? The shifting the k naught samples is shifted in the frequency. Got it, my students? For that, when the frequency is shifted with the k naught samples, the exponential, that to the positive exponential with the k naught samples, is multiplied for the time signal. Previously, when we check the x of t minus t naught, if the time is shifted after applying the Fourier series, the frequency x of k is multiplied with the exponential, that to negative exponential jk omega naught, and whatever the samples it is shifted in the time is getting in the t naught. Now the x of t is a time signal. The Fourier series is x of k minus k naught. We get that, means the frequency shifted with the k naught samples. It is multiplied with the e power positive exponential jk. That k is now the k naught omega naught into t. The time is multiplied with the positive exponential with k naught, and the time is shifted, the frequency is multiplied with the negative exponential with the t naught. Got it, my students? Now see here, by using the same expression in the proof, check the z of k is equal to 1 by d the integral dx of t z of t power minus jk. You have to prove this one. See, 1 by d the integral t, take the x of t, or the z of t is e power jk naught omega naught dx of t. Substitute this total function, and e power minus jk omega naught t. And see here, the two exponential, the bases are same. Add the powers here, x of t and e power. Take the minus as a common. In this k omega naught k and omega naught k, and here is a plus. So keep the minus here, the minus into minus plus. Omega naught t is both the common, and k naught is there. So this looks like the same function of analysis equation of the Fourier series, exponential Fourier series, but instead of e power minus j k omega naught t, the k value is k minus k naught. So x of k minus k naught. Once again, you can see a little bit confusion, I think. I will explain. So the third property is frequency shift property. It's the third one, frequency shift. Okay. What they're saying, that you can take the z of t is equal to e power plus jk naught omega naught t x of t. Apply the Fourier series for the signal, you'll get the shift in the frequency. That shift is k naught samples is shifted. So I take the k naught is the positive exponential. So proof. Second, the Fourier series, the exponential Fourier series, z of k is equal to 1 by t, the integral t, x of, not the x, z of t into e power minus, see here the k is k. Here also the k and here also the k1. K omega naught t dt. This is a formula for the exponential Fourier series, that to the analysis equation. So replace the z here, 1 by t, the integral t, and the z of t you can take the e power plus j k naught omega naught t x of t into this function we have multiplication part minus e power j k omega naught t d. Now the bases are the same, you can add the powers here, 1 by t, the integral t, x of t you can keep here, x of t into e power. Take the minus j is a common, and here the omega naught t is also common in the both the terms. If I am taking the minus j, having only the k here in this one, k this function, and minus minus into minus is a plus, minus here the k naught. So observe here the z of k is there, e power minus jk. Here the k is there, the frequency function is a z of k. Now the k is here, the k minus k naught, and the x of t signal. So I count the exponential Fourier series, you get x of k minus k naught. The frequency is shifted. Got it, my students? Okay. The frequency shift property. When the frequency is shifted, the exponential is added, the positive exponential is added for the not added, sorry, multiplied for the positive exponential, multiplied the time, and the time is shifted, negative exponential is multiplied with the frequency signal x of k. Okay. Next, fourth property, scaling property. Scaling, to scaling in the time scaling. The z of t is equal to x of a into t, x of a into t. The Fourier series, you can z of t k is equal to x of k. Even if it is multiplied with a into t, there is no change in the frequency. That is the same thing, will get the x of k. Why it is means the Fourier series is analyzed for the periodic signals. So x of t is a periodic, then z of t is equal to x of a t is also periodic. Remember, my dear friends, is also periodic. And if t is a period of x of t, so if I am taking the x of t is a signal, this time period is a t. Now I am taking the x of a into t is a signal, the scaling property, a is a scaling for the time. What is the time period? T by a. When the t is a capital T, the time period. For a t, the time period is a t by. What is my difference? Similarly, this is for the time, and for the similarly the frequency, the x of k is equal to. For x of k, or otherwise similarly the frequency x of t for the x of t. Why I'm saying here is the CA, the x of t only. Let it be the x of t into e power minus jk omega naught is a frequency into dt. It's a formula for the exponential Fourier series of the analysis equation. Integral t 1 by t is there. And here the omega naught for x of t, the frequency is omega naught. What about when the x of t is scaling with the x a of t? The frequency is when the time is decreases here, when the time is multiplying the a t by a, and now the x of a t means is becomes of a into the multiplied factor a into omega naught. A into omega naught minus. Similarly, if the frequency x of t is omega naught, the frequency of z of t x of et will be a into omega naught. Since t is multiplied by a factor of a, so t is multiplied by a factor of a, and the frequency is also multiplied by the factor of a here, the omega naught. You remember these two functions, and now we can go for the prove the x of z of t is x of at to get the z of k is equal to x of k. Same over participants. So I will prove this one. So x of a into the fourth property, scaling property, x of at, you can take and apply the Fourier series, you'll get the x of k, x of k. Now, the analysis equation is saying that z of k is equal to 1 by t, the integral t, z of t, e power minus jk omega naught t dt. Jk omega naught t dt. So it is at stake is a z of t, and you can prove that it is a z of k is equal to x of k1. Proof. Now what is the z of t here? The 1 by t, the integral t, and z of t is x a of t, and e power minus jk omega naught t dt. Got it, my dear friends? So now I am taking here the time is in scaling with a, the time is scaling with a, the t is becomes of t by a. So x of t having the time period is a t, and the xa of t, the time period is a t by a. And x of t, the time frequency is omega naught, and xa of t, the frequency is a into omega naught. So replace the a of t is equal to some dummy variable m, and t is equal to m by a. Dt is equal to what? Dt is equal to dm by a. Remember, let this function. So the 1 by t, the integral t. Now I'm changing this x of at is the x of m. As of at is equal to m, I assume. E power minus jk omega naught, and t is a m by a. T is m by a, and dt is a dm by a. So a can write in the outside. This is only the let function is equal to, when the a is here, the t by a only. Okay, the t by a. So 1 by t by a is a at is a t by a is a time period. For t is the time period is a 1 by t. And integral t xm and e power minus jk omega naught by a. Totally can write this as omega naught by a into m into dm. So whenever it is a, you can try at, the frequency is multiplied with the a. So a get cancelled, e power jk omega naught m into dm. See, this function is the same function of z of k, is nothing but the replacing the x value as xm. It becomes of x of k. Nothing is changes. X of k. The time period is a t by a, and the omega is the frequency is multiplied with the a get cancelled. Again the same function. The k omega naught is there, and the time period is changes t by a. The t by x of k is equal. The scaling property says. Got it, my dear friends?